Based on the examples we've seen so far, it looks like most differential equations have many solutions. Here's just one example. So this differential equation is a simple model of an object warming up or cooling down in a 20-degree centigrade room. This differential equation is basically due to Newton. And it turns out that this differential equation has all of these functions as solutions. Well, we can check that these really are solutions just by plugging it into the differential equation. So d capital T, d little t. I haven't given units for little t. It kind of depends what the units for little t are, depend on what the units for this constant are, but let's not worry about time units. Taking a derivative, we get, remember this capital A is a constant, so when we take a derivative with respect to little t, we get minus capital A over 10 times e to the minus 1 over 10t. And comparing that to the right-hand side of the equation, minus 1 over 10 times capital T, which is ae to the minus 1 over 10 little t plus 20. So this whole part is capital T minus 20, because that's part of the differential equation over here. When we simplify that, that does indeed equal d capital T, d little t. So all of these functions are solutions, but it might be a little concerning that this differential equation has so many solutions, because after all, if this differential equation is describing a physical situation, shouldn't there be just one solution? I mean, if you set up a situation, some definite thing happens. If the differential equation is really describing the situation, then shouldn't there just be one solution that matches the thing that actually happens? Well, to get a handle on what's going on here, let's actually sketch a few of these solutions, capital T. If you look at them, they're all exponentials with exponential decay because the exponent is negative here. And they're all, so we have a decaying exponential that's then stretched by some amount because of this capital A that could be any constant, and possibly flipped vertically as well if capital A happens to be negative. And then it's shifted up 20 because of that plus 20. So what that's going to look like is, right, an exponential decay decays towards 0, but we're shifting up 20, so we're going to have this horizontal asymptote at 20. And everything is going to decay towards 20, so like this, or like this, or if it starts below 20, it might look like this, or like this. And what's different about all of these functions? Well, one way of describing what's different about all of these functions is that they all start at t equals 0, or indeed any time. They all start at a different temperature. So what's different about all of these functions is that they all have a different initial value. So what separates all of these is different initial values. And, you know, in retrospect, actually that isn't a surprise because, you know, I said this differential equation describes an object cooling down or warming up in a 20 degree Celsius room, but what determines whether it cools down or warms up? Well, it depends on whether it starts warmer than the room or colder than the room. So, of course, the actual behavior of the situation depends on where you start out. So, in retrospect, that makes sense. So let's see what happens when we actually specify an initial value. So let's say, for example, that the object starts out at, say, 5 degrees. So that means at time 0, the temperature is 5. Okay, but look, we have a formula for capital T right up here. We can plug time 0 into this formula, and we get capital A times e to the minus 1 over 10 times our time value, which is 0, plus 20. And look, the result that we get by doing that is an equation where the only unknown is this constant a. So we should be able to solve this equation for a. So subtract 20 from both sides. I guess simplify first. This e to the whatever, that's e to the 0, so that's 1. So we get a plus 20 equals 5. And so a is negative 15. So the solution to the particular solution to the differential equation that satisfies this initial value is capital T of little t is negative 15 times e to the minus 1 over 10 little t plus 20. Okay, so for this particular situation, because the object started out at a temperature cooler than the room, the exponential gets flipped, and that means that it's actually starting low and increasing towards this asymptotic value of 20. So it seems like what a differential equation has lots of solutions, but what selects just one of them is some sort of initial condition. Okay, let's look at another example. So here is a second order differential equation. Second derivative of y minus 5 times the first derivative of y plus y equals 0. And it turns out that solutions to this equation all look like this. Some constant times e to the 2x plus some other constant times e to the 3x. And I'll let you check that. So what kind of extra information do we need to narrow this down to just one solution, right? We have a 2-parameter family of solutions here, so lots and lots of solutions. What sort of extra information will narrow all of these solutions down to just a single solution? Well, given our experience with the previous example, it seems like what we need is an initial condition. So for an initial condition, let's say that y of 0 is 2. Okay, well, we know, again, based on our experience from the previous example, we know how to use this initial condition. We can use our formula for y of 0. We have this formula for y of x, so just plug 0 in there for x, and we get c1 plus c2. But there's a problem here. We have two unknowns, c1 and c2, and only one equation. So this actually isn't enough information to narrow it down to a single solution. In fact, it is enough information to narrow it down to a 1-parameter solution, because we could use this equation involving c1 and c2 to eliminate either c1 or c2 in the original family of solutions. But still, it's not a single solution. So we need a little more information to narrow it down to a single solution. And there are a few ways you might add information to this setup to produce another equation. You might specify the value of y at a different x value, or you might specify not just what y is at 0, but also specify what y prime is at 0. So let's add a condition by saying that y prime of 0 is 2. Okay, well, just like we used y of 0 being 2 to get an equation, we can use y prime of 0 equals 2 to get another equation. So let's calculate y prime. Do that up here, I guess. Y prime is 2 times c1 e to the 2x. This 2 in front is coming from the chain rule, plus 3 times c2 e to the 3x. And then we can plug x equals 0 into that to turn this initial value for y prime into an equation. So we get 2c1 plus 3c2 equals 2. And now taking these two equations together, you see that we have a system of two equations and two unknowns. And in fact, they're both linear equations, so linear algebraic equations. And so there is going to be a solution for this. All we need to do is solve this system of equations. So maybe let me move this equation over here, and while I'm at it, let's multiply this equation by -2. I'm just setting things up to eliminate C1. So we get -2C1 minus 2C2 equals -4, and then add these equations. The C1s cancel, and we get C2 is -2. And now that we know what C2 is, we can go back and find C1. So say using this first equation, 2 equals C1 plus C2, but now we know that C2 is -2, and so C1 is 4. So now we know C1, we know C2, and so we get a single solution. Y of x is C1, which is 4, times e to the 2x, plus C2, so -2 times e to the 3x. And so this is the single solution that satisfies the differential equation and these two initial conditions, that y of 0 is 2 and y prime of 0 is also 2. Okay, you can kind of see a pattern here. What makes this example different from the previous example is that this equation is order 2. You might guess that if you have an order n equation, then you should need n initial conditions. One for the 0th derivative of y, one for the first derivative of y, and so on, until you get enough initial conditions. And indeed, that is the case. We call that setup an initial value problem. So when we have a differential equation where the nth derivative of your unknown function y is given by some combination, some function of the independent variable and the 0th through n minus first derivatives of your unknown function, add to that initial conditions for the 0th to n minus first derivative of your unknown function, we call that an initial value problem, or IVP for short. One important thing to notice about the way that this is set up is that all of these initial conditions for the derivatives of y all have to be at the same x value. If you have different x values, that's not technically an initial value problem. So it's actually important that these all be the same for theoretical reasons that we'll get into later. On sort of a practical level, it makes sense that these are all that these should all be the same because, right, if your differential equation is describing some physical system, having all of these x values be the same really is the independent variable would be time in that kind of situation. And so what you're specifying here is y at some initial time and y prime at some initial time and so on. So what you're really describing is the complete state of this system at an initial time. So it makes sense that we require all of these x values for our initial conditions to be the same x value. Notice that at this point, although based on our experience, this is a good way to set up our initial value problems, we don't actually have any guarantee that an initial value problem actually has a unique solution, or indeed any solution at all.